All right, everybody, in AP Calc BC, welcome to lesson 4.3, Intro to Vectors. And this lesson takes what we've learned about parametric equations and applies it to something called vectors. We'll learn all about that new vocab term. If you've taken a physics course, then you may be familiar with the idea of vectors. And this is really where we kind of see the usefulness of parametric equations, because so far in our first two lessons of this unit, all we've done is see that there are initial equations in terms of t, and then done all that we can to get rid of it, right? We've talked about how do we find the x and y version of the equation without the t, how do we eliminate the t? We talked about how do we find the dy dx for the slope of the tangent line on the graph. So on the graph, again, without really taking into account the t. We talked about the second derivative, and we talked about the arc length. None of those really have to do with t. You know, some of them for the derivative, we had t in the equation, but like on the graph, it's applied just on the graph. It's not really about t. But vectors allow us to take this to the next step where we can actually use parametric equations to make vectors, and we'll take a look at that today. So we're in College Board's Unit 9, and Lesson 9.4 is defining and differentiating vector-valued functions, and that's what we're going to be doing today. So methods for calculating derivatives of real-valued functions can be extended to vector-valued functions. And with that, I'm going to pause and take us over to the notes. All right, so this notes comes along with a handy-dandy formula sheet. I either gave this to you in class or it's attached on Schoology so that you can see all the things that we need to know here. And on an AP test, you will not get a formula sheet. So these are things that you'll need to know. The first part is covered by what we already learned in previous lessons in this unit. So we've talked about the dy dx and the second derivative. We start with dy dt over dx dt, and the second derivative is the derivative of that over dx dt again. And then this is just a description of dx dt and dy dt. Dx dt is the rate at which the x coordinate is changing with respect to t, or the velocity of the particle in the horizontal direction. Dy dt is the rate at which the y coordinate is changing with respect to t, or the velocity of a particle in the vertical direction. When we combine those, we can make the dy dx, or we can keep them separated and call them vectors. So if we write the x equation, comma, the y equation, kind of like an ordered pair, but instead of parentheses, we put kind of these angled brackets. This would be the position vector. If we use the first derivatives, it would be the velocity vector. And if we use the second derivatives, it's the acceleration vector. A vector is usually visually shown as an arrow. And if you look at the notes sheet for today, you'll see examples of that. We're going to kind of fill this in and show you exactly what this means, but we're going to break this down into its x direction and its y direction, and then together, kind of like the hypotenuse of if this was a right triangle, that creates kind of the angled version of the vector. All right, so dy dx is the rate of change of y with respect to x, or the slope of the tangent line to the curve, or the slope of the path of the particle. That's what we've looked at already. The second derivative is the rate of change of the slope of the curve with respect to x. And then we've got these two formulas down here. We've got the square root of dx dt squared plus dy dt squared. This is the speed of the particle, or the magnitude or length of the velocity vector. That's the length of the arrow that we're going to be talking about. And then if you do an integral, this is going to be the arc length, right? This is what we also looked at in the last lesson. Arc length, in this lesson, we're also going to call this the distance traveled by the particle, because if you think about some sort of curve that we might map using parametric equations, that is technically mapping, the path of a particle. So the distance that the particle travels could be considered also the length of that arc, or, if we stretched it out straight, how long would it be? So that we're going to be using that again as well, okay? So that's some of the formulas we're going to be looking at today, but let's see if we can apply this, many of the things we've already done, but in vectors. So it's just kind of writing parametric equations in a new form. Example 1, a particle moves in the xy plane so that at any time t, the position of the particle is given by these formulas. these equations. A, find the velocity vector when t equals 1. Okay, so velocity vector means that we're going to be looking for x prime of t and y prime of t, or dx dt and dy dt. We don't care about finding the dy dx this time because we're looking for the vector. All right, so I'm going to find x prime of t. So we're going to have 6t squared minus 10t. And y prime of t is going to be what? 8t to the third plus 3t squared. All right. And if we wanted just the general velocity vector, we could write that like this. And that would be the general velocity vector. It's kind of like an ordered pair again, but we can have t's in there. This specifically wants when t equals 1. So let's find the x prime of 1. So it's going to be 6 times 1 squared minus 10 times 1. That's going to be -4. And we have the y prime of 1. Don't mind my weird looking y there. And we've got 8 times 1 cubed plus 3 times 1 squared. So what we got? 8 plus 3, so 11. So the final answer is going to be in the cornered brackets, the angled brackets, -4, comma, 11. So that's breaking the motion down into the x and the y motion, or x and the y velocity separately. And together, that makes up the velocity vector. That doesn't tell us where the particle is at the point. This is saying that at this moment, when t equals 1, we've got a motion -4 units per time in the x direction and +11 in the y direction. All right, letter B, find the acceleration vector when t equals 1. So now we're looking for the second derivative in terms of t for the y and the x. So we're just going to keep taking a derivative. So 6t squared minus 10t. We take the derivative, we get 12t minus 10. 8t cubed plus 3t squared. We take the derivative, we're going to get 24t squared minus 6t. And again, we could just kind of write those into a vector like we did up here, but we want to know when t equals 1. So I'm going to plug in 1 for t. So that's going to be 2. And we got 24 times 1 squared minus 6 times 1. That's going to be 18. So we end up with 2 comma 18. And that, again, that's breaking the acceleration down into the x and the y motion. Okay? All right. How do you find the magnitude or length of a vector? So for this part, if we were going to do a position vector, we're going to break it down into its x and its y direction. And we know that the x direction would be x of t and the y direction would be y of t. And together that makes up the vector, right? So that's this arrow. So if we wanted to find the magnitude or the length of this arrow, we're going to use the distance formula, or you can think of it as the Pythagorean theorem, where we have x of t squared plus y of t squared inside of a square root. Okay, and that's going to give us kind of the overall magnitude of the vector. Magnitude just kind of says, okay, we don't want the x and the y separate anymore. Give me one number. Give me the overall magnitude. Just like the singular number that represents the motion, but it doesn't tell us what direction it's going in. That we lost the x and the y that tell us the direction. It's just going to give us the length of this arrow. Okay. Let's take a look at the velocity vector. I feel like the velocity makes a little bit more sense in this context because we're talking about actual like movement now. But we're going to think about this as dx dt and dy dt, or x prime of t and y prime of t. So the magnitude of the velocity vector is going to be the same idea. And that's where our arc length formula comes from, right? Acceleration vector, same idea. Oh, the magnitude of the velocity vector is called the speed of the object moving along the curve. So it's just kind of like if you're driving your car or riding a bike or something, or even just walking, right? You can have a certain speed in your car that would be on your dashboard, but that's not going to tell you what direction you're moving in. You'd have to look at the compass for that part. Okay, and then we've got the acceleration vector. Again, same exact idea. We've got our x double prime of t and our y double prime of t. And so we're going to have the square root of x double prime of t squared plus y double prime of t squared. Okay, and those are things that will be on that formula sheet that you have separately. Example 2, a particle moves in the xy plane so that any time t for t greater than or equal to 0, the position is given by this set of parametric equations. Find the magnitude of the velocity vector when t equals 3. All right, so we're talking about the velocity vector. So if we look up here, we're going to need dx dt and dy dt. So I'm going to find those first. So it's going to be 2t plus 5. The y prime of t is what? 1 over t squared plus 4. Oops. 1 over t squared plus 4 times 2t, because we've got to multiply by the derivative of the inside. In other words, what do we get? 2t over t squared plus 4. Okay. So if I was going to kind of sketch this out, here's my visual version of the vector. The x motion is being represented by 2t plus 5. The y motion is 2t over t squared plus 4. So we could write that as a vector, which I might just do down here just so that we have it. And that has the x and the y motion separated. But we want just the speed or the magnitude of the velocity when t equals 3. So the magnitude of the velocity is going to be the square root of 2t plus 5 squared plus 2t over t squared plus 4 squared. And we want to know this when t equals 3. So I'm going to plug in 3 for t. So we get 2 times 3 is 6 plus 5 is 11. And we have 6 over 13. Okay, and you know what? Let me move out of the shadow. I'm just going to stop right there because I can. Okay, we're allowed to stop as soon as we have an answer that could be typed into the calculator with just common operations, which is what we have here. I could get an approximate version of that answer, but I'm just going to leave it like that. Okay, so that is the magnitude of the velocity when t equals 3. It is positive, so we are going to be moving in a certain direction, but we don't know what that direction is. Okay, so let's take a look at example 3. Particle moves in the xy plane with these equations where 0 is less than or equal to t is less than or equal to 2 pi. The path of the particle intersects the x-axis twice. Write an expression that represents the distance traveled by the particle between the two x-intercepts. Do not evaluate. Okay, so first of all, we need to know what we're looking for. We're trying to find the distance traveled. Like we said on that formula sheet, that's just another way of saying arc length. So we're going to be wanting to fill in that arc length formula. So I'm going to write that out real quick over here. We said S equals the integral from a to b of dx dt squared plus dy dt squared dt. Okay, so we kind of already know the x and the y equation. So we're going to have to take the derivative of the x and the derivative of the y so that we have the dx dt and the dy dt to plug in here. But we need to know the bounds of our integral. And the question tells us that we need to find the two x-intercepts so that we can do that. What do we know about x-intercepts? At x-intercepts, the y value is 0, right? Think about the x-axis. Anywhere on the x-axis, if you think about ordered pairs, it's something comma 0, right? 2 comma 0, negative 3 comma 0, etc. So I'm going to write that down. At x-intercepts, y equals 0. So we know what we need to do, right? We need to plug in 0 for y and see what t is. So 0 equals 1 minus 2 sine t. I can subtract 1 to the other side, divide by negative 2. And I need to think about my unit circle for a second and figure out when the sine, what angles have a sine that equals to 1/2. And that's going to be at pi over 6 and 5 pi over 6. Yeah, because it's the y value. Yep. So there are our two values, right? That's between 0 and 2 pi. So it's between the two x-intercepts. So we're going to use that as A and that as B. So we've already got the pi over 6 to 5 pi over 6 part set up. Now we need to know what is dx dt and what is dy dt. Okay, so that shouldn't be too bad. So let's separate this out here and try to figure this out. So we got dx dt. That root 3 is going to go away. So we're going to have, what is this? Cosine becomes negative sine, and it's just going to cancel out with that negative. So it's going to be 4 sine of t. And the dy dt is going to be what? The 1 goes away. Derivative of sine is cosine. So it's going to be negative 2 cosine. There we go. And so now we know what to plug in for dx dt and for dy dt. The question says, do not evaluate. So we found the integral here. That happens a lot when we get into these more complex looking integrals that are going to be really hard to evaluate. Instead of making us type them into a calculator, that just a lot of questions just say, hey, if you have an integral that represents the solution, then you can just stop there. The tricky part is actually making sure it's set up right. But we got it. Okay. Okay, we learned earlier in the year that a particle moving along a line is at rest when its velocity is 0. If a particle is moving along a curve, the particle is at rest when its velocity vector is 0, 0. That makes sense, right? Because that means the x motion is 0 and the y motion is 0. So that means we're actually at rest. So let's figure out example 4. A particle moves in the xy plane so that at any time t, the position is given by this set of parametric equations where t is greater than or equal to 0. For what values of t is the particle at rest? So we got to figure out when is the velocity vector 0, 0. So remember, the velocity vector is built with x prime of t, y prime of t. So that's what we're going to have to set equal to 0. So if we have x of t, we could say x prime of t is going to be 6t squared minus 15t plus 36. I did that wrong, didn't I? That should be 30t. 6t squared minus 30t plus 36. The y prime of t is going to be what? 3t squared minus 6t. And we want both of those to be set equal to 0 separately. And we're going to compare the answers and see if any of the t's match up. So let's see what we got. We got 0 equals 6t squared minus 30t plus 36. I can factor out a 6 from each of those terms. And t squared minus 5t plus 6 factors to t minus 2 and t minus 3. So our answers are going to be t equals 2 and t equals 3. So that's the two times that have an x velocity of 0. Let's check the y prime. I'm going to factor out 3t. And so I get t equals 0 and t equals 2. That's the two times that have a y velocity of 0. And would you look at that? When t is 2, we have a situation where the particle has an x velocity of 0 and a y velocity of 0. Therefore, it's at rest. So our final answer is t equals 2. Final example, example 5. A particle moves in the xy plane in such a way that its velocity vector is given. At t equals 0, the position of the particle is 7, -4. Find the position of the particle at t equals 1. All right, we know what to do here. We're going to think about the x and the y separately. Well, I know what to do here. I think we can figure this out, but I'll help you realize that you know what to do if you're not sure. So for the we're going to think about the x and the y separately. At t equals 0, the x position is 7. We know the velocity, or the first derivative, in the x is 3t squared minus 4t. And we're looking for the position in the x at 1. So our x of 1 is going to be equal to the x of 0, which is 7, plus the integral from 0 to 1 of 3t squared minus 4t. Right? Because we're moving from 0 to 1, and that's our first derivative, right? That's the fundamental theorem, right? So what do we got here? We got 7 plus t cubed minus 2t squared from 0 to 1. And if I plug in 0, it's all going to cancel out. So I'm just going to plug in 1. And we're going to end up with 7 plus 1 minus 2, which is 6. I'm going to do the same exact thing now for the y's to find y of 1. So I'm going to start with the -4. That's when t is 0. And we're going to smooth along the velocity to when t is 1 inside this integral. And so we've got, what, 8t cubed plus 5. And so let's start to evaluate this one. So we got 2t to the 4th plus 5t from 0 to 1. All right, so once again, if we plug in 0, it's all going to cancel out. So I'm only going to worry about plugging in 1. And we end up with -4 plus 2 plus 5, so we get 3. So our final answer is a position, right? So we are not going to write it in a vector form. It's actually an ordered pair, just like the one that was given up here. So it's going to be 6, 3, right? Because we got the x value, the x coordinate when t is 1, and the y coordinate when t is 1. So that is the answer to the question, and that is the end of the notes. All right, so just as always, thank you very much for watching. Let me know if you have any questions. Good luck with the worksheet. Have a great day.